Good morning. At least I think it's still morning. Close enough, anyway. It's morning somewhere. Every time I see Marinus' presentation, I'm a little bit upset by his presentation. Yeah. Just a little. You see, my Corvette was silver. It actually was a 64, but it looked the same as that 63, and it was a silver one. And, you know, just to think about, you know, whatever. I come from Rochester, Minnesota. And I thought, many people say, why Rochester? I mean, Rochester developed the, you know, System 3, the 32, 34, 36, 38, AS400, IBM I, et cetera. And a lot of people have asked over the years, why Rochester? First of all, Rochester is a small farming community. I don't know how else to describe it. It's located just about in the middle of the U.S. Minnesota, the state we're in, is on the border with Canada, so we do tend to get snow and cold weather. Yes, like especially this year. But I thought I'd give you a little bit of background, and it sort of explains why these computer systems all came out of Rochester. It was back in the 1950s. IBM had moved from being just essentially a U.S. company prior to that to becoming more and more of an international company, lots of different countries and so forth. And one of the things that was pointed out to them is that all of the headquarters, all of the development, all of the work that was done were all done in the state of New York. It was a New York-based company because Tom Watson Sr. had founded the company in New York. And so there was a thought that maybe they should have development locations somewhere else in the country and perhaps somewhere else in the world. And they decided that they should have at least 2 more locations in the US. One on the West Coast, one somewhere in the middle of the country. On the West Coast, they picked San Jose, California, and they built a big facility in San Jose, big IBM development facility and manufacturing. Looking for a place in the middle of the country was more difficult. And they hired a firm to look at all kinds of different cities and come up with a listing of all the possible cities. And they came up with a list of 75 cities where they thought IBM could put a manufacturing facility as well as a development laboratory. One of those cities was Rochester, Minnesota. Now, if you look at it and you say, well, what did Rochester have going for it? The answer was nothing, okay? It was very small at that time. It was about 30,000 people. I mean, today it's about 120,000, which is still fairly small. It had one major industry. It had the Mayo Clinic, which is a medical facility. It was there at the time, still is. It's huge today. Nothing else. If you looked around for skills, I mean, for example, for a development facility, you need engineers and programmers and so forth. You know, could you hire them from the local, you know, community? No, of course not, right? Because it was just too small. And so people say, well, how come it ended up in Rochester, Minnesota? Well, the answer is pretty simple. During the Second World War, Tom Watson Jr. was a co-pilot on a plane. It was a general's plane flying around basically most of the time in China, most of Southeast Asia, and they were in areas of China. And he was the co-pilot. The pilot of the plane was the son of the biggest banker in Rochester, Minnesota. And the two of them became very close friends. And so when the banker in Rochester, Minnesota discovered that Rochester was one of the names on the chart, Tom Watson Jr. got a call from his friend saying, put it in Rochester. And Tom Watson Jr. said, okay. And they did. And it's still there. Okay. So it was selected with absolutely no thought in mind as to the surrounding, where you're going to get the talent, anything like that, right? It's a farming community. We're a bunch of farmers, right? Okay. So they had to give it something to do, you know, because we're going to manufacture some things and we're going to develop some things and so forth. So they decided to give it the old card machines. Remember those old counting machines, right? So sure enough, Rochester starts manufacturing these card machines, right? And they put in place a development facility a couple years after manufacturing, and they started developing brand new punch card machines, right? Really pretty exciting stuff. And somebody then in Rochester, the development part of it looked at it and said, well, you know, who buys these things, right? And it's basically people who can't afford a computer. I mean, during the 1960s, computers were so expensive, only very large companies could afford to buy them. And in fact, you never bought them, you actually rented it from IBM, right? But these things were incredibly expensive. And if you were a small or a mid-sized business, you did work with an accounting machine of some kind, or some sort of a tabulating machine, or whatever it was. And so they said, well, if we can really reduce the cost of these machines, and we could put some sort of a control unit with this thing, right? Similar to an accounting machine kind of a control unit, we actually could develop a computer system for small and mid-sized businesses. Well, how do you reduce the cost of one of these big old, tabulating machines, these old big old card punch machines? The answer is simple. You just take metal out of it, right? How do you do that? You create a small card. The smaller the card, the cheaper the less bulk goes in it, it's cheaper. So they worked with some folks, actually, you happen to be in one of the research laboratories, who were pushing for some small, ugly-looking little card, right? And so they made the punch card smaller. And so a lot of people in Rochester that were working on this, they had hired a lot of mechanical engineers. They were happily building, these mechanical devices. They then said, well, we need something to control it, right? We need some electronics of some kind, right? And nobody knew anything about building electronics, computers, whatever it was. So they went out to other IBM locations and said, hey, anybody interested in coming to Rochester? Kind of silence, right? But there were a few foolish people who said, well, yeah, we'll go there, right? And one of the people they hired was a fellow from Endicott, New York. Now, Endicott built some of the low-end models, if you will, of the System 360 back in the 1960s. And the one they brought out was in charge of the System 360 Model 30, okay? Which I'm sure nobody remembers that thing. But the Model 30 was one of the low-end kind of computing systems. And so he came out and he said, well, yeah, I know how to build something that looks sort of like a Model 30, and we take a little bit of cost out of it. And so that's what they built, not knowing anything different. It'd be nice to be able to program this thing, wouldn't it? It's kind of a concept there. Well, what do you do? Well, how do you program an accounting machine? Well, those old tabulating machines had these boards with all the yellow wires. By the way, I never knew why they were yellow. I kept asking that question, why does everybody use yellow wires? And nobody could ever answer it. But if you ever see one of these in a museum, they're really kind of ugly. It's one of these great big boards, here's my payroll, here's my accounts receivable, here's my, whatever. And you'd plug it into the machine, it would do that particular application. Well, IBM came up with an ingenious way of moving that kind of programming to their 360 line of machines, and specifically the low end. And they created this brand new piece of software that they called Report Program Generator. It first ran on a System 360 Model 20. And so, not knowing any difference, the folks in Rochester said, that's it, okay? And because it didn't work on the big cards, those big 80-column cards, it worked on these new small cards, they called it RPG-2, right? And that was it. And I have to tell you that the corporation, first of all, would have never let Rochester build a computer if they knew they were building a computer. Because if you looked in IBM, the computer systems were being built in Poughkeepsie, they were building Endicott, there's some things going on in Kingston. These are all in New York, okay? That's where computers are built. People in Rochester build accounting machines. So sure enough, they sold this as these new low-cost accounting machines with a controller that runs RPG, which everyone knew was not a programming language, right? It wasn't really a programming language, it was some strange thing. And they got it through the corporation. And one of the nice things, in business everywhere is it's easier to get forgiveness than to get permission, right? And that's what happened. And pretty soon they discovered that the same thing ran this funny thing called COBOL. And everybody says, you mean that's a computer? Literally, that's how they got out the so-called System 3. That was the development, without really knowing what they were doing, okay? I took a summer job with IBM. Not that I wanted a summer job with IBM, but my father convinced me that it would look good on a resume, and it was only 3 months, and as he said, I wouldn't work there the rest of my life anyway. Never let him forget that. Never. Anyway, I was really impressed with the level of people and what they were doing. And the reason for it, as in hindsight, I guess I didn't understand it at the time, but in hindsight, the people in Rochester did not know what they could not do. And that's the secret of Rochester, is that every other place, if you said, I want to do whatever, oh, we tried that already, right? It didn't work. We know that doesn't work. Oh, by the way, this is the way we did it the last time around. We have to do it the same way because we were successful. You know, one of the bad parts about success is if you're really successful and you're asked to do a follow-on to it, you do the same thing, right? I mean, that's human nature because it worked, right? So I thought it was great. I ended up going to work for them after I graduated and got to know the people that were running this program. This is a pretty small organization and everything like that. And they said, look, we have a problem. We have a lot of mechanical engineers. They know how to build these devices. We have electrical engineers that can, you know, put the circuits together. We have some programmers, although we're hiring more, but you know, we don't have anybody that really understands systems. We don't have anybody that really knows operating systems, how to put these things together. Why don't you consider going back to school? So I was kind of dumb at the time. You know, I thought, well, yeah, I can do that, right? So I took a leave of absence and I went back to school and I studied computer architecture and systems and all kinds of wonderful things, right? And meanwhile, in Rochester, they were busy building these computer systems and, you know, shipping out the so-called System 3 and whatever, and discovering it was really a computer. And so when I finished, when I graduated from school and walked in the door, I met with the head of all these systems and all the future kinds of things, and he says, I got a job for you. Really, what's that? He says, I want you to design the follow-on to the System 3. Now in those days, IBM thought that the life of a computer system was exactly 5 years. In other words, every 5 years you had to come out with a new system. And in fact, if you go back historically and look, that's what IBM did. They would roll new models and so forth, you know, from the 360 to the 370 to the 390 to, you know, whatever. If you look at all the mainframes, every 5 years, 6 years, whatever, they came out with a new one. And so they said, you know, we need this new thing, you know, in about 5 years. Can you design it? Of course I can. So here we have a location that doesn't really know much about computers, okay? And they give it to somebody who's never designed a computer, ever, right? And we built it. Now it was scheduled to come out in 1975. It didn't come out until 78, because what happened is there was a recession in the early 70s in the world, actually. And IBM shut down hiring. We couldn't hire new people to work on this thing. So it got delayed to 1978. We called it the System 38. And it was a strange computer. Because as a lot of us talked about it, we didn't know what we couldn't do. And a lot of people, you know, I sometimes look back in time and say, how come we're still here? I mean, think about it. That's 35 years ago we introduced this silly thing. And you're still here. I'm still here, right? What did we do that kept this thing going for 35 years? Because clearly one of the things that happened during the 70s, 80s, into the 90s, mostly in the 70s and 80s, is there were hundreds and hundreds of companies building computers all over the world, okay? I always remember, you know, the Japanese computer systems of the 1980s. You know, there was a thought they were going to take over the world. I mean, I knew of at least 20 different Japanese companies that were all building computers. And by the way, they're building multiple models. If you wanted to go out and buy yourself a computer system just to run your business, you had thousands of models to choose from, right? There were companies all over Europe, all over America, all over, you know, Asia, you know, everywhere these companies were all building these specific computers. And of course, what happened? They're all gone. Every single one of them is gone. We are now down to a choice. If you're going to go out and buy a business computer, you have a choice of 4. There's only 4 left. And most people say, well, wait a minute, there's more than 4. I can buy more than 4. No, you can't. There's only 4. And I thought, why only 4? What's the purpose of these 4s? Why did those 4 survive? And those 4 survived because each one of them had a completely different design point. Well, not maybe completely different. There's a couple of them that are pretty close. But they had a specific design point. They meet a specific need. And when you're selecting one of those, you really need to understand what it was designed to do. Okay? And not everybody does that, because a lot of people look at it and say a computer is a computer is a computer, right? They're all the same. No, they're not. Okay? So what are the four? Well, the oldest one is 50 years old next month. You're going to see the celebrations. IBM mainframe, introduced in April 1964. And next month, you're going to start seeing IBM celebrating 50 years of the mainframe, right? Now, think about the early 60s when it was designed. What kind of business computing was done? Okay? It was batch. It was all batch processing, totally batch, right? I mean, nobody thought of attaching a terminal to these things, right? Strictly batch. And so the fundamental design of the mainframe, of the 360, the architecture, the hardware, everything is to do super batch processing. And even the way they measured performance, they measured it in MIPS. MIPS, just how fast you can speed the engine. In batch processing, the faster it goes, right? The more work you get through it. And even today, they still talk in terms of, MIPS that they ship on these things. Well, in the late 60s and starting in the early 70s, people said, we really want to start attaching terminals to these with different users and things like that. But the mainframe wasn't designed to do that. So what did they do? They had to put a patch on it. Patch, a software package that they put on it. CICS. Anybody old enough to remember CICS? How about the IMS database? Those are all you remember. I can see you. Yeah, you're saying that. These are transaction processors, because they didn't design the thing to do transaction processing. And clearly, they've made tremendous progress over the years, especially in areas like virtualization and so forth. And today, the mainframe is a fabulous system. It really is, right? It runs a lot of businesses around the world, okay? So you can buy a mainframe. It's arrived, okay? What's the second one you can buy? Unix. Now you're saying, wait a minute, there's a lot of Unixes out there. No, there's not. Unix is Unix is Unix, okay? They come from different vendors. But if you look at the concept of Unix, it was designed in the late 60s. It's not 50 years old, it's only 45 years old. It was designed in the 1960s to be a very simple, very low-level operating system that you could put pieces on top to customize it to do what you wanted it to do, okay? It was designed for a single user workstation. That's the idea behind it. So, think about things like, I'll call it security. What was security for a Unix system? Lock the door on your way out. Okay, but that's it, right? And so if you look at Unix over the years, obviously it's evolved, right? We have various vendors developing Unix. Oh, by the way, there's also Linux. Why is Linux growing so fast? Anybody know? It is, it's growing very fast. You saw, this huge investment IBM's making in it. Well, it's because the standard Unix is going down, okay? In fact, that started about almost 10 years ago. 10 years ago, it was worldwide a $25 billion business. Last year, it was $9 billion. So fewer and fewer people are buying the standards, right? From HP or Sun or IBM or whatever, and more are moving to Linux. So it's coming down. Linux is basically going up, but it's all Unix, okay? That's available to you. 45 years old, okay? What's the third one? We got mainframe, we got Unix. What's the third one? Windows. Windows, right? Buy Windows. It also is 45 years old. I'll get you a few blank faces here. Wait a minute, Windows is newer than that, right? We know it's new, modern, newest, latest, greatest operating system, huh? Well, let me tell you a quick story, okay? Back in the 1980s, when Windows first came out, it was DOS, of course, disk operating system, right? And it had a very thin layer on it to provide what they talked about as the Windows interface to it, but it was basically DOS. And so Microsoft needed a full operating system. And so they teamed up with, of all companies, IBM. And together, IBM and Microsoft were developing a new operating system. The operating system was called OS/2. Anybody remember what happened to OS/2? We could spend the next hour talking about how we screwed that one up. Oh, by the way, I keep saying we, you know. I officially retired from IBM 5 years ago so that, you know, I wouldn't have to stand up in front of audiences and address them and things like that. They still think I work for them, but now I'm able to work with business partners. I meet with a lot of user groups. I'm a big fan of user groups, especially trying to get some new ones started in various parts of the world, and also various colleges and universities. So I couldn't do that. I didn't have the time when I was working for IBM, but my agreement with IBM is I said, when you need me, call me, and they still think I work for them. So anyway, but it works out. But I still say we. I think you get it tattooed, you know, there's something. So I still say we, okay? It turned out that neither of the two teams could work together. In other words, there was a Microsoft development team, there was an IBM development team, and they were constantly at each other's throat. You know, do it this way, no, do it this way, fighting. At the time, which was in the early 90s, I was spending a lot of time in Austin, Texas. Austin, Texas is where OS2 was being developed. And the reason for it is my assignment at the time in the corporation was to lead a team to come up with the architecture of Power. In other words, we were looking for a new processor for the AS400 in those days. And the goal that I had was to lead a team of highly technical people from all over IBM and create an architecture that could be used across each and every IBM platform in the future, from the future on. It's called Power. And that's exactly what we're doing with it today. I'm going to come back to that in a minute. But while I was down there, I heard all the infighting that was going on between IBM and Microsoft, right? Well, in 1991, I can't remember the month, I was sitting in Austin with this team of people, and we heard of a proposal that came in. I want to share it with you. Bill Gates approached the head of OS2, and he said, look, this is not working. We just can't, our development teams just can't work together. I have a proposal. He said, you give me OS2, I will complete the development of it, and in exchange for that, you, IBM, will own half of all Windows products. Now, put yourself in the position of the IBM person making that decision. Okay? What's your decision? And then think of the opposite, because that's what IBM did. Oh, that was a no-brainer. I mean, that was absolutely a no-brainer. I mean, Microsoft knew how to market these things. They knew, you know, I mean, Windows was successful. It was going to be incredibly successful in the future. And for IBM to have own half of it, basically own half of the thing, right? And just to say, okay, here, you develop OS2, and, you know, we'll bring it out as some operating system, and we'll each share it. You know, it'll be a PC operating system. No, IBM said, oh, no, we're not going to do that. We're going to develop it ourselves. And so IBM said, it's ours, we're going with that, okay? So all of a sudden, Microsoft was caught without an operating system, okay? Well, fortunately, just about everybody in the industry was abandoning their operating systems, right? I don't care whether it was HP or it was the one that they latched onto was actually digital equipment. Digital equipment had come out with a brand new alpha processor, a RISC processor, really a good one. And they said, you know, we've had these VAC systems for years. Now, I've been associated with universities most of my life. And, you know, we always used VAC systems running a VMS operating system and so forth. I mean, that was kind of a staple for almost any university. And Digital said, we're going to get rid of it. We don't need it anymore. Any of you folks that are out there on VAC systems, good luck, you're on your own. We're going to go to a new modern operating system called Unix. And they did. They made the move. So suddenly there's a group of developers who were responsible for the VMS operating system. This was a great operating system. And they had no job, okay? Now, by the way, the VMS operating system was developed back in the late 60s. It was, you know, about the same time as Unix, and it was very similar to Unix, okay? It had a little bit more function built into it than a Unix platform, but it was designed for a single user workstation, and it became very, very successful over the years. So all of a sudden, there's a group just outside of Boston, Massachusetts, that had no work. They were out of work. So one of them was interviewing with Microsoft saying, hey, you got a job for us, whatever it is. They said, sure, we need to build an operating system. And he said, well, you know, I got a whole team back at Digital that are looking for work. Are you interested? Microsoft said, sure. They hired the whole team. Took them to Redmond, Washington, and went to work on a new operating system, okay? A couple of years later, I think it was 94, 95, Microsoft announces Windows NT. Remember Windows NT, the announcement of it? I mean, that was a full-fledged operating system. It truly was, right? It wasn't DOS with something on top. It was a real operating system. Well, Windows NT, the first version, I think, was like 3.1 or some crazy number like that. It's one I remember. Once in a great while, it'd blow up. Yeah, okay. When it did, it put up VMS error codes. Slight problem here. Yeah, it was VMS. Digital looked at it, said, we got you. You stole our operating system. I give all kinds of credit to Microsoft for marketing, right? Gates in particular. He went to Digital and says, I got a deal for you. Tell you what we're going to do. We're going to put Windows on Alpha. And that's the only RISC processor you're going to get. You're going to be our high-end Windows platform. You're going to make all kinds of money. And by the way, you, Digital, will be our #1 Windows partner in the whole world. And all you have to do is sign VMS over to me. And they did. Digital owns VMS. I mean, they do. They own the rights to VMS. So Windows NT was really VMS from the late 1960s. Windows today is based on that model. So Windows is 45 years old. Okay? Oh, by the way, and a little trick that programmers like to do, if you take the letters VMS and you add one letter to it in the alphabet, you get WNT. That's how it was named. That's not a coincidence. It was the next generation of VMS. They just added a letter to it and called it Windows NT. So you can go with Windows, a 45-year-old operating system. Or you can go with the newest one, #4, which is IBM I. It's only 35 years old. So when I hear all these people talking about this old, tired operating system, right, it's the newest one you can buy, right? Sorry. Okay. And it's also very different. It wasn't designed as a single-user workstation. It wasn't designed as a batch machine. What was it designed to do? Well, in the 1970s, everything was transaction processing, right? I mean, terminals attached to whatever. So sitting back in Rochester, we're coming up with a new system. We said, well, let's design the architecture for transaction processing. It's the world's only system currently available that was exclusively designed for transaction processing. So when somebody says to me, well, you know, this thing's going to go away any day now, right? When do you anticipate it's going to go away? I said, well, when we no longer need transaction processing. Well, what do we use transaction processing for today? Everything. As we look to the future, what are we going to use? Transaction processing, okay? It's the world's most advanced transaction processing system. And in fact, some of you may remember way back when we came out with the first AS400s, and you'd run transaction workloads, and you say, wow, this is really great, okay? And then you run a batch workload, and you say, what went wrong? Right, it never had a very powerful processor, which was the problem, which is the reason I was leading this team to come up with Power, right? And it was never designed to have a powerful processor to do batch processing. It was designed exclusively for transaction processing. Now, one of the things that people over the years have never really understood is, how do you build a system to do transaction processing? So let me tell you another story. I'm full of stories. You probably gathered, you know, you like my slides, by the way. One of the things that happens in IBM is that before you come out with a new major product, you have what's essentially a peer review. You have other laboratories, other experts come in and review what you're doing, okay? So we were intending to announce this System 38, as it was going to be called, in 1978. And getting ready for that in 1977, information about it was sent out to other laboratories. including IBM Research. Now, IBM Research is clearly one of the leading edge research organizations in the world, still are today. A fabulous research organization. And they were one that was charged with reviewing new products that were coming out. So back in IBM Research, some folks sat down and they said, okay, we've got all these specifications and so forth on this new thing that's going to be called the System 38. Let's see, you know, if this thing makes sense, whatever it is. And they quickly concluded that it would never work. They looked at it, they said, these people don't know how to do a computer. Nobody builds computers like this. They said, it won't work. IBM is going to be horribly embarrassed. They're going to announce this thing, and it's going to die because here's how the world builds computers. Here's how you build mainframes. Here's how you build Unix systems. Here's how you build, you know, everything. And this strange thing over here will never work. And oh, by the way, we've tried it before and it didn't work. We saw in 1977 the biggest audit that certainly Rochester's ever seen. Because all of a sudden, we had technical experts from all over IBM assigned to come in, right? And if any of you have been to Rochester, you know, we sit in these funny blue buildings, right? And there's one of the blue buildings that sticks out in the parking lot. And that particular building was put in place to build disk drives, okay? One of the things that happened in IBM is that there was a division between San Jose building disk drives and Rochester building disk drives. And so they were trying to figure out, you know, and their headquarters was in San Jose. And of course, what they decided is, you know, who gets what disk drives? And so they thought, well, you know, big guys get big disk drives. So all of the huge platter disk drives and everything like were in San Jose, and the ones that would never have any future, you know, like the 5 1/4 inch and whatever, went to Rochester. Anyway, yeah, exactly. When they discovered that, they actually moved the whole thing to San Jose. But there was this building, and you know, if you can picture this thing, you know, with the concrete floors in it, it's not finished. The building was just completed. There was nothing in it. Absolutely big, empty warehouse kind of building, you know, sitting there. They decided that's where to hold this Inquisition. And so they set up metal tables. I mean, this is crazy. With metal chairs, right? And for 3 weeks, you know, we had this panel grilling us about how could we be so stupid as to build this thing, right? And so, you know, I had the wonderful opportunity to address this panel on multiple occasions, right? And I'll tell you about one of those, which maybe will help explain what I'm talking about. One of the things we did is, of course, we were running all kinds of simulations and so forth on this particular system. And so we had a lot of statistics on, you know, for example, how many instructions you execute before you actually switch to another user. Remember, this was a single processor, so that we weren't doing multi-processors at the time. So what I had to do is switch from one user to another in a single processor, right? And so we were showing some of those numbers, and I was showing some of the numbers, and I was pointing out that on certain workloads, we would execute roughly 1,000 instructions, and then we switch to another user and execute another 1,000, and then switch to another user, and so forth. And all of a sudden, one of the people on the panel, don't remember who it was now, said, wait a minute, that's your problem. And I said, what do you mean that's our problem? And he says, well, you're not getting any work done. I said, well, we're executing 1,000 instructions. No. He says, you don't understand. He says, in the mainframe, to switch from one user to another takes about 1,000 instructions. Takes 1,000 instructions. And what you have to do is you have to take all of the internal address registers and so forth. Remember, these are all virtual address, virtual memory machines. You got to clear them all out. You got to bring in all the new addressing tables for the new user. You got to load all this up. It takes 1,000 instructions at that time in the mainframe just to do that transition. And then you can do useful work. He says, you're not doing any useful work. And I said, well, we don't execute 1,000 instructions to do switch from one user to another. He said, well, how many do you do? 1. Have you ever looked over a group? Right? I remember that look. That's the only thing I remember about this Inquisition, is this strange look I'm getting. And these are top people in IBM. These are really bright people, okay? And there was just this blank, did you say 1? 1. And they say, what is that instruction? Branch. Branch. So, what do you mean? I said, yeah, just branch to the other user. We have a single level store, right? Users all in there. I just branch to the code and start executing. And they go, oh, but wait a minute, you have a problem. What's my problem? Well, anybody can branch anybody else's code. I mean, you've got multiple users in there. You have no protection. Sure I do. How do you do that? Well, all of these are in objects. In objects? What's this object business? When I was in school, I actually did work for my graduate degree on a new memory structure which became single level store. And since I had to demonstrate it would work, and IBM at the time wouldn't let me take the university mainframe computer and modify it to show that it could work, which I never understood, I had to come up with a simulation to do that, right? And so I got very knowledgeable in simulation languages, and one of the simulation languages at that time was SimScript. And the idea with SimScript is that anything that you didn't really care what was inside or couldn't see it, you put it in an object. And you just defined what inputs were, and when you gave it that input, what the output was. And I thought that was fabulous. And a couple of years later, SimScript was rebranded as Smalltalk. It was the first object-oriented language. So I came back to Rochester saying, wow, what a great concept. Let's put this thing in objects, right? Nobody can see in the object. It's protected, right? By the way, it's never had a virus. Within IBM, we always wanted to say this, system is virus-proof. And of course, the lawyers would never let us say that. We said, there's never been a virus. Nobody's ever seen a virus on the I side. Yeah, if I'm carrying around Windows code or something, I can carry a virus, right? But I can't carry it on the IBM I side. And they wouldn't let us call it virus-proof. We could call it virus-resistant, right? Whatever. But that's one of the reasons for it, right? Okay, fine, it's in an object, right? And you say, well, now wait a minute, can't anybody break into that object? Or what happens if you happen to branch to an object even that you own that's a data field? Well, we also protect each one of these. We say, all right, this is a program object, this is a data object, this is a whatever, and we only allow certain operations against certain types of objects, okay? Wow, how do you enforce that? Our hardware does. Now here's a key point for today's IBM I. It's secure. It's built in. It's not an operating system with a chunk of security on top with an interface between, right? Because as long as there's an interface between, if you can get to that, you can break into any system. We're going through something in the US now. It's kind of fun to watch. One of our major discount stores, right, Target, lost millions of credit cards. It's going to cost them millions of dollars to recover that. And of course, every movie that we watch on hackers, they're these very sophisticated with, banks and banks of screens and typing away and, whatever. And when you find out who really hacks into these systems, they're 12-year-old kids. There is nothing to it. I was in Malaysia not long ago, and I was doing a presentation to an IBM user group down there. And in the same conference center, there was another conference going on, and the title of the conference was Hacking into the Cloud. It was here's how you do it, right? Because basically every public cloud out there is hackable and will be hacked. There's absolutely nothing to it. I mean, I put my photos, family photos, or pictures have been taken here, right, of various game animals and kinds of things we were doing over the weekend. I put them up in the cloud so my whole family could go see them, right? But I don't put any of my personal financial information in the cloud. And that's one of the reasons why, as we talk about things like pure systems, and you start talking about cloud-based, these are private clouds, these are corporate clouds, these are protected clouds, right? They're not public clouds, okay? That's the difference with it. So one of the keys that we end up with is we end up with something that's important for business. It's like secure, right? It keeps running because I can build these things to be extremely reliable. I've got the hardware protecting it, so nobody's going to get at it, right? I mean, you'd have to get in and modify the chipset in order to be able to break into one of these things, okay? It's really that solid. And it's built for transaction processing. It's the most efficient transaction processor out there. And so when people say, why does this exist? It's because it meets the needs of business. I mentioned that one of the things we did in the early 90s is I led this effort to come up with what became Power Processor. The goal of that, which I bought into right away, is that should be the only processor used across all IBM products. And even more important to that, my philosophy since that time has always been that IBM should have one system. Only one system. IBM only needs one system, okay? Oh yeah, I can have small ones and medium-sized ones and big ones and things like that. But I should be able to have a single system where I can configure all 4 of those environments, since there's only 4 of them, right? And I should be able to put those things together all in one system. And so we set on a plan within IBM, and where I spent a good share of my time, working to get the corporation to go with basically one system to merge these things together. In 1995, we introduced this first 64-bit RISC processor, we called it. That was Power, first implementation of Power, 64-bit Power, into the AS400. 2 years later, 1997, we took an AS400, whole thing, frame, okay, ripped off the labels, pasted on a label that said RS6000 and began to sell it as an RS6000, okay? If you were in Rochester in the manufacturing facility and you looked at these things without the covers on, you had no idea which was which. When they put the final covers on, then you knew, oh, that's an RS6000, that's an AS400. They were 100% identical, no difference. But of course, from a marketing standpoint, they said, well, we can't have that. And so even the processors were actually identical, everything was identical, they had to give them different names, right? And so we said, well, get rid of the 2 models, come out with a new model that runs either or both, right? And of course, Linux was the next one basically coming along there. And from 1997 until 2008, think about it, we finally got them together. 2008, we came out with Power Systems that runs these, all 3 of these, right? Currently 3. It took a long time to convince IBM this was a good thing. I often talk about IBM as an aircraft carrier. IBM is an aircraft carrier, okay? Steaming along, right? If you want to change IBM, think of yourself sitting in a rowboat alongside of that aircraft carrier, and you're pushing the aircraft carrier, right? If you keep pushing, eventually you'll get it to turn, right? But it might take a little while, right? Okay. So in the early 2000s, we finally got to the point where we're saying, okay, yes, we're merging these things together. By the way, I want the mainframe in there. There's no mainframe in there. How come, right? In 2001, we finally convinced IBM to put all these things together, use the same hardware. Because once you start using the same hardware, now I can start using pieces of software out of the operating systems. By the way, what big piece of operating system did we pick out of AS400, OS400? The virtualization. We put the virtualization layer under AIX and under Linux. That's where it comes from. That's the virtualization in there actually came from the System 38. I mean, that was that far back. By the way, the System 38 was the world's first totally virtual machine. It was a piece of software. It had no relationship with its hardware. We didn't call it virtual because that wasn't a term in those days, right? We called it technology-independent machine interface, right? Some ugly thing like that. But it was a totally virtual machine, which says it could actually run on different hardware platforms, which is another story that I don't have time for. But in early 2000, the corporation was convinced, and they made an announcement. And the announcement was, we're going to use common hardware across all of our platforms. We're going to use common software across all of our platforms. Now, software, we're talking about some operating system code. We're going to use common middleware across our platforms. We're going to have a common management system. You heard about it this morning, right, where you can manage, right? They announced it, 2001. And of course, once the announcement materials went to our lawyers and came back to us, we weren't sure what we announced. But that was the announcement. And what does the world remember about that announcement in October of 2001? We changed all the names. To make the point, every name was named E-server, remember that? I-series, P-series, X-series, etc. And that was the point at which they said, we're going to bring them all together. And that's where we really got serious about starting bringing these together. Internally, the operation that we were working on was called Eclipse. And it was spelled E-C-L-I-P-Z. IP and Z systems were all going into the box, okay? Today's Power System runs ZOS. If you step into Poughkeepsie, they will scream and holler, no, 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 it doesn't, no, it doesn't, no, it doesn't, we have to have our own. I still maintain one of these days there's going to be a surprise announcement that lo and behold, you can have ZOS in these boxes, okay? But at the moment, they're still holding out. They want their own stuff, right? Okay, fine. That's a marketing decision, not a technical decision, okay? So we had 3 of the major operating systems, right? Whoops, we were missing, wait a minute, what were we missing? We were missing that PC operating system that we had. It was called OS something or other. So why don't we get Windows, right? So about that same time frame, we had a call from Microsoft saying, would you come out to Redmond, Washington and talk to us about Windows on Power? We said, sure, we can do that, right? So we went to Microsoft and they said, we want to have Power, we want to run Windows on Power. And in fact, we're creating a 64-bit implementation of Windows. I think it was 32 bits in those days. And we see your 64-bit implementation of Power technology as a platform we want to be on, because we see that really as the high end of the market. If you want big Windows servers, you're going to be on something like Power. Now, by the way, at the same time, they were also looking at Intel's Itanium, which was their 64-bit implementation, right? And so one of the things that they were proposing is they were going to be porting Windows, a 64-bit implementation of Windows, to Itanium first, because Intel obviously is their close partner, right? And once they made that port, one of the things you find is that some of the old operating systems, including ours, were all written in assembler or some low-level operating system language that was unique to IBM or whatever. So once you port over, much like we did to the 64-bit RISC, you write it in more common languages. We use a lot of C++, Java, and so forth. And they were going to be doing the same sort of thing. So once you made the first port, the second port is about a 10% cost adder to it. In other words, it costs you about 10% of the cost of the first port. And so they were going to make that port. They announced to us that their schedule was a 3-year time frame. And this was 2000, 2001 kind of time frame. So 3 years, and then a year and a half later, they would introduce it on Power. Great. 2005, roughly, we're going to have Windows running on Power, running right alongside of all of our other systems in our Power system. This was really great, right? I've told the story many times. I was sitting there. I told them that our experience is that doing a port this significant takes about 5 years. That's what it took us. It took us 5 years. They laughed. They said, we're in the PC business. We move pretty fast. You guys are IBM. You're kind of old and tired, and you move slower. And so it takes you 5 years. We're going to do it in 3. They did it in 6. It took them 6 years to do the port of Windows to Itanium. Quick show of hands. How many of you are running Windows on Itanium? I usually can find one in the audience. Seriously, I can. Itanium's a fabulous processor. I teach processor design at the university. And I always use different examples. And if you look at Itanium, it's really a great processor. It's a great design. And you look at the x86, and my students say, who would ever build something like that? Because it's been patched over the years. I mean, it's been added on and whatever. What happened? Well, the market changed, right? I mean, there's this other little company at the time called AMD. And AMD says, wait a minute, we can take this little 32-bit thing and we can stretch it, and we'll call it 64 bits and we'll start selling. And they took, what, 30% of Intel's business or something like that. So Intel, pretty much abandoned that. Almost nobody bought Windows on Itanium. And so Microsoft came back to us and said, we're not going to move to Power because it just doesn't make it, we'll have the same problem, right? It doesn't make any sense. So that was the point at which we said, well, wait a minute, why don't we just put Intel processors under the covers of our, these converged systems? And that's what began what we're talking about as pure systems, okay? That was sort of the beginning of the whole thing, is we'll have Power processors, we'll have Intel processors, we'll have whatever we need under the covers. And so that's how we were going to achieve Windows running in this same environment, right? Over the years, we've had others, and I know I'm pushing my time here. Do I have time for another, my famous, does anybody remember when IBM bought Sun Microsystems? Anybody remember that? No? Don't you get the news down here? We were invited to Sun Microsystems a couple of years ago, and Sun gets their hardware from Fujitsu. And Sun was very concerned that Fujitsu would not be able to keep up with the latest level of hardware technology, processor technology, in the same way that Intel and IBM do. Because doing processor technology these days is just incredibly expensive. And the expense is mostly in the manufacturing. I mean, it's just hugely expensive to manufacture these things. As a result, you have to sell, a gazillion of the chips, right? And of course, in power, we do. There's a good possibility that the vehicle you drove in today, even though you're probably sitting idling in traffic for quite a while, had power processors somewhere in it, okay? We sell a lot of them in automobiles. But they were concerned that nobody'd be able to keep up. So they were saying, why don't we source our processors from either Intel or IBM? And they looked at, of course, they run an Intel x86, and they were looking at the time, this was a couple of years back, they were looking at Itanium, and they thought that was a possibility, and Intel would certainly sell them processors. They asked us if we'd do the same, and the answer is yes. We had a proposal, we'd sell them any power processor that we had, latest generation, we laid out our roadmaps, we did the whole thing for them. In fact, IBM even volunteered, we'd build the boxes for them, we'd build their servers, we'd build Sun servers. And obviously with Sun, names and logos and everything on it, we'd supply them with any hardware they wanted, okay? And we started to look at it. And so we had Solaris, their operating system, running on power, and it looked pretty good. And one of the other things I find as I travel around the world, a lot of financial organizations will have IBM I as the core, and it's surrounded by Sun servers, Solaris servers, right? It seems to be the most popular Unix out there as far as financial kinds of things. And I've often made the comment, my wife and I have 3 sons, and they're all engineers, which I've never understood. 2 of them are, kind of pretty logical, picked really good versions of engineering to go into. The third one, the youngest one, is not very bright. He's a computer engineer. And he's a Unix bigot. That doesn't come from me, that's my wife's side. He's a Unix bigot, and his favorite Unix is Solaris. And so over the years, he kind of, educated me on the differences in the Unix, and he's probably right. Solaris is probably the best Unix of the Unixes, right? Now he's big on Linux and that sort of thing too. But anyway, we looked at it and we said, this is really great. Now it turned out that Sun said, we're going to stay with Fujitsu for a while. But all of a sudden, this whole concept with Sun kind of made sense. So one Friday afternoon, I get a phone call, and it says, we just bought Sun. Keep it under your hat. We haven't announced it. IBM bought Sun. We're going to announce it on Monday. This is Friday afternoon. Oh, wow, this is great. I mean, I know I can name a half a dozen major banks in the world that are going to be overjoyed with this because they have, power systems, and then they have all these racks and racks and racks of Sun servers, right? And we had worked with some of them to be able to incorporate all those virtually into some of the power systems running Solaris, right? But they're on Solaris. That's what their code is written in. Instantly, we're going to see a huge uptake in Solaris running on power, right? Monday morning, I go to my news feed, right? Oracle buys Sun. What happened, right? Well, over the weekend, a decision was made by the board of directors of Sun. The board of directors asked for big amounts of money. I don't know if you use the term golden parachute, because they would be gone, right? Management would be Oracle suddenly. And so the management team and the board of directors and so forth all said, well, we want big buyouts. And IBM just doesn't do that. And to me, that's really a good thing for IBM. They just never do. And so IBM would say no. Oracle obviously says yes. And so they sold to Oracle. And that's how they ended up with it. So we kind of lost out on Sun. I haven't given up on them yet, so we'll see what's happening. Point is, that's the future. We're going to see even more of this consolidation. Our systems are far too complex today. Our environments are too complex today. The whole concept of pure systems is really aimed at that. When pure systems came out, almost everyone said it's the new AS400, right? It's integrated, right? We're seeing that going forward in, whether it's clouds, and when I talk about cloud computing, it's really private clouds, it's really corporate clouds built on some of these things. Certainly the mobile area. Analytics is going to absolutely change whole industries, absolutely change them. In Rochester, Minnesota, we still have the Mayo Clinic, which is this huge medical facility. And we're working very closely with analytics with this big medical facility. And part of the reason for it is because their view of the future, especially of drugs and drug interactions. I mean, think about it today, you know, as far as a cancer patient, there's a selection of different drugs available, and the physicians come up with some combination of those, whatever, right? They say that's pretty old-fashioned. What they're really doing now is they're actually taking an individual's DNA and creating a drug specifically for that person. In other words, it's a drug to treat whatever it happens to be that's designed for one and only one patient, okay? And when you start looking at all the different interactions and how you put these together, right, there's a huge amount of analysis that has to go into this. And this whole concept of analytics suddenly makes that very feasible. And so we're starting to see that in the medical industry. Law is going to be in for a huge change. As far as, you know, analyzing various court cases, you know, past kinds of things and so forth. You know, you don't need a whole room full of lawyers going through the books, right? You need about 30 seconds on one of these machines, right, to find all of this sort of thing, right? And so as we go through various industries, we're going to be seeing a major impact of analytics. And so, you know, that to me is one of the real big changes. It'll be sort of rolled out very much like we saw business intelligence in the late 80s. There were a few people that got into business intelligence and said, well, you know, I'm not sure what we're going to do with this, but maybe it has some use. And it took a few years, and all of a sudden it spread. Analytics is going to follow that exact same pattern over the next years. And of course, as you heard, IBM has now laid out a roadmap, unbelievably so, until the year 2025. It's an I roadmap to 2025. I mean, when I first joined IBM, we couldn't talk about anything until it was announced, and even then, much of it wasn't until it was shipped, right? You know, it was one of those strange things. So this is unprecedented for IBM to go out to 2025. And by the way, it doesn't fall off a curve. You know, we don't kill it in 2025. But to keep people, you know, knowledgeable on what we're doing and the growth of this thing, you know, like you saw, you know, 7.2 comes next month, right? Power 8 is around the corner. You know, by the way, there is a 7.3, or maybe it's going to be called 8.1. You know, they argued on 7.2. Should we call it 8.1 or call it 7.2? And I'm sure the argument will go on in the next one. But these things are all on the drawing board. You're seeing a lot of new function added. This thing isn't anywhere near dying, right? So it has a function, and I'm really tired of reading articles about any day it's going away, right? So thank you very much. I think there's food.